So we're going to wait just a minute or two to get started so that everybody has a chance to log in. Usually people need just a moment after the top of the hour to get themselves fully onto the Zoom session. Well, welcome everyone. We're going to get started in just a moment. Okay, we are at 1 minute after the hour, so we'll go ahead and get started. Welcome to the Air Sea Fluxes from Space webinar series. Today we have Jacob Wenegrat from the University of Maryland, who's going to talk about effects of air-sea interaction on submesoscale processes. And I'll let you take it away, Jacob.
Great, thank you. Yeah, I really appreciate the invite to come talk. As I was putting the talk together, I realized that a lot of the sort of effects part of air-sea interaction on submesoscale remain pretty speculative, but hopefully it'll be good for conversation at least. It's useful to start by thinking about what we define as a submesoscale. So, of course, we often talk about it in terms of relative length scales, 100 meters to 10 kilometers or so. But it's often more informative to think about it in terms of a dynamical definition, which we define using the Rossby number and Richardson number. So under this definition, the submesoscale are those scales at which the Rossby and Richardson number are order 1, in contrast to larger scale or smaller scale motions. And that definition reflects the joint influences of planetary rotation, nonlinearity, the fact that stratification is important, but these motions are much more fully three-dimensional. And I think that is useful as a reminder that the submesoscale is not purely a length scale. So it is not simply a matter of sort of scaling down our mechanisms of air-sea interaction that we know from the mesoscale down to the submesoscale. These are dynamically unique scales. But at the same time, there is a mismatch between the ocean and atmosphere dynamical regimes, but they communicate through the boundary in terms of their imprint on fluxes in terms of length scales. So showing here, a logarithmic length scale in the middle, and the ocean sort of typical mid-latitude scales at the bottom, and then the atmosphere scales at top. So the atmospheric mesoscale dynamically is very similar to the submesoscale. And so I think it is sort of an open question to some degree. What is the right range of length scales to think about when we are thinking about air-sea interaction? And here is a case where thinking about length scales may be more informative than pure dynamical regimes because of this mismatch between ocean atmosphere scales and dynamical regimes. And so I just wanted to highlight one of the things. We had a workshop in the fall on air-sea interaction coupling at submesoscales. And one of the ideas that came out of that was the possibility of defining what we call the air-sea interaction submesoscale, which we argue should be a bit more broadly defined than purely the ocean scale. So really spanning from 100 meters up to maybe 100 kilometers or so. And the reason for this is twofold. First, we think this ought to encompass the ocean submesoscale, at least for now, down to the finest scales of the submesoscale, although perhaps those stop mattering quite as much for air-sea interaction. But then it also ought to scale up to encompass those lengths of scales in the atmospheric side where the response remains in disequilibrium. So if you blow wind across a front, the atmosphere will take a sort of longer downstream length scale to equilibrate to that SST variability, and that will extend really into the atmospheric mesoscale, larger than the ocean submesoscale. Now, I want to highlight a few things about this range of length scales, which I think are particularly interesting from an air-sea interaction perspective. The first is that these scales sort of span the inflection point between forward and inverse energy cascades on both sides of the fluid. And so if we want to think about how this fine scale variability might have upscale impact in particular, that I think is worth keeping in mind, that it may depend in some sense on where it falls in terms of forward or inverse cascade. The second is that the sort of effective footprint of bulk flux formulas, they're averaged in time, and so they have an effective spatial footprint, falls somewhere in this ASI submesoscale. And I think it remains sort of unknown how important that is in our picture of these interactions. And then finally, from my perspective, one of the more interesting aspects is that this range of spatial scales, both for the ocean and atmosphere, we expect the dynamics to sort of violate some of the common assumptions that have been used to develop our process level understanding of air-sea interaction. Things like steady state assumptions are likely incorrect, small aspect ratio, and others. So I'll come back to that point a bit more. So what do we know about air-sea interaction at the submesoscale? Well, we know that some of the mechanisms from larger scales do transition down to smaller scales. So showing kind of cartoons here of the current feedback on stress and the thermal feedback on stress. And I'll come back to both of those in a bit more detail throughout the talk. So I've structured this talk as sort of hitting on three areas of work on this topic that have come out of our group. The first is how the current feedback on stress can actually modify the Ekman buoyancy flux, which is a really key determinant of submesoscale dynamics at fronts. Next, we'll talk a bit about how models and now observations do show that this thermal feedback is modifying the atmospheric boundary layer structure and hence winds, even at these very sharp fronts. And finally, I'll end on a note of how important the sort of direct eddy potential energy flux at fronts can be. So both of these first two mechanisms focus on modulation of the surface stress or the surface momentum flux, but at the same time, there's a direct flux of eddy potential energy, which shows some results that suggest it could be equally important as well. Okay, so the current feedback on stress, it's probably well known to the folks on this call that the bulk stress formula ought to be formulated in a surface relative frame, so involving the difference between the surface or 10-meter winds and the surface currents, as shown in the top line here. And that allows you then to define a perturbation stress tau prime simply as the total stress minus this component involving only the wind, so the sort of Earth relative formulation. Now, one thing I'll note is that this is really just a kinematic result or definition. It's entirely local or 1D, so this mechanism ought to be active or robust at all scales. It doesn't depend on the adjustment, say, of the atmospheric boundary layer like the thermal feedback does. Now, an example of this is shown here. So this is an idealized simulation. It's a fairly large domain. It's run at submesoscale permitting resolution. Here's a snapshot of SST at left, vorticity in the center panel. So there's lots of submesoscales here, order 1 Rossby number. And then this is forced. There's a surface buoyancy loss and then a moderate wind stress towards the northeast, as shown by the gray arrow here. And then what's plotted in the right panel is the zonal component of that perturbation stress, that is that bit which is being generated by this current feedback, normalized by the background zonal component. And so sort of by definition, all of these fine scales imprint on the surface stress. That's not a surprise. Zooming in here on one cyclonic cold core eddy, shown here, so it's Rossby number of about 2. The zonal velocity is shown in the second column, and this is anti-correlated with this perturbation stress. And so this anti-correlation is what gives rise to a negative wind work through the so-called eddy killing effect that's been the subject of quite a bit of study, both at the mesoscale and at smaller scales by people like Lionel Renaud. But what I want to highlight is that this is a baroclinic eddy, and so there's also a buoyancy gradient associated with these currents. And you can see here's that zonal perturbation stress, and I'm plotting here at right the meridional buoyancy gradient. And these tend to be correlated. And that opens this avenue for perhaps another mechanism of air-sea interaction through the Ekman buoyancy flux. So the Ekman buoyancy flux is defined really simply. It's just the Ekman transport dotted into the horizontal buoyancy gradient. Here's a nice cartoon from some of Eric's work showing a wind, in this case down a front. You can think conceptually of that as being associated with the horizontal Ekman transport advecting dense water over light water. And the magnitude of this at submesoscale fronts can be really large, so equivalent to sort of order 10,000 watt per meter square surface heat fluxes. Really emphasizing, I think, that this can be much more important to the evolution of the boundary layer at very sharp fronts than, true air-sea heat fluxes. More importantly, I think, is that it's also sort of directly generates a flux of potential vorticity. And one thing I want to highlight is that although we often think in this sort of cartoon or schematic way of development of an actual horizontal transport, in terms of the PV dynamics, this is sort of an instantaneous diagnostic of the flux. You don't actually have to set up this advective transport in order to get the PV flux. Now, looking at the definition, it follows fairly directly that you could break this into two components, a tau bar component involving just the sort of wind only formulation of the stress, and a tau prime component from this current feedback. Looking at that in the same simulation, so here's the total EBF field. In the middle column is the tau bar part, the EBF tau bar, the sort of standard formulation. And then this part due to the current feedback is shown at right. And I'm putting this in terms of, again, an equivalent heat flux just for comparison. So this the magnitude of this change is somewhere in the sort of 25 to 30% range generally. So it's in some cases a sort of significant correction to the total EBF. It's most important when the surface currents are large or the winds are weak or fronts and winds are not aligned. So this top column here, top row rather, is showing winds largely across a front. The bottom column is winds down a front where there's loss of PV from the boundary layer, but this current feedback effect is acting as essentially a source. And because it tends to be the case that the thermal wind shear and surface currents are aligned, that is, the thermal wind shear is in the direction of the surface currents, this correction tends to be of the sense to be a source of Ekman buoyancy flux to the mixed layer, or equivalently a source of PV. It's not single sign. There are places where they oppose each other, but those tend to be much weaker than the cases where they're reinforcing each other. And so this acts as this source in the distribution. So here's a distribution of equivalent heat fluxes across the simulation and counts, and you see it tends to be negatively skewed, a source into the mixed layer. What that means is that for this simulation, that leads to about a 50% decrease in the mean Ekman buoyancy flux at top. This is a function of time here, shown in terms of a heat flux. And again, the Ekman buoyancy flux can be sort of directly translated into a PV flux. And in this simulation, so one run without the current feedback and one run with, we see about a 50% increase in the amount of PV injection when you include this current feedback effect. So now it remains really challenging to really fully assess the impact of this sort of bulk change on submesoscale dynamics. And part of that is because one of the routes which it could be speculated that this might change is through the change in symmetric instability. And we're not currently able to run such a large domain at fine enough resolution to resolve SI, or symmetric instability. But so I'll just lay this out as a speculative argument, which is that we know from very extensive work that the Ekman buoyancy flux sets the rate of PV injection or destruction depending on alignment with the front. So down front winds tend to destroy PV. That allows the growth when you have negative PV. So this is a snapshot from an idealized large eddy simulation that's initialized with negative PV. Very quickly, sort of order inertial timescales in that negative PV region, you have this fast growing, very fine scale instability associated with these banded overturning cells. So this is the X vorticity, so in and out of the page, showing this banded along isopycnal structure that's characteristic of SI. And the rate of this SI growth is set by the Ekman buoyancy flux. It's extracting energy from the background thermal wind flow through what's called the geostrophic shear production. These are associated, these overturning cells, with a lot of vertical shear. And if you zoom in on one of these simulations, much finer view of it, what happens is you develop a secondary Kelvin-Helmholtz instability between the cells. So actually a lot of the energy which is coming from the background thermal wind shear through the geostrophic shear production of the submesoscale is then being directly dissipated. And so a snapshot of kinetic energy dissipation rate is shown in the bottom right. And so again, sort of speculating, this, I think, suggests a potential pathway for the current feedback on stress to modify boundary layer energetics. So a reduction of the loss of the EBF, or loss of PV through the EBF, which is what these feedback tends to do, would tend to damp this geostrophic shear production rate and hence dissipation. And to put that in context, we believe there's sort of emerging evidence, I'd say, that SI mixing could be an important sort of global contributor to boundary layer turbulence. So there's certainly observational evidence from Eric DeSaro and Leif Thomas and others in major Western boundary current systems like the Kuroshio and Gulf Stream of very significant enhancement of boundary layer turbulence due to SI, and then more recent work which is suggesting that this is also of global importance. Now, the change that's just happening here through this mechanism turns out to scale quite similarly to this sort of eddy-killing wind work. So if you compare the relative importance of changing this Ekman buoyancy flux dissipation to changing the surface wind work, it scales as the ratio of these two velocities, the change in geostrophic velocity over the boundary layer depth to the total surface velocity. So in the case that you have a surface velocity which is being set by thermal wind shear through the boundary layer, this becomes order one. That is, both mechanisms are equally important from a scaling perspective. This is in a paper in JPO. Again, a lot of the sort of effects here or potential effects on the submesoscale are left as speculative based on what we know about the role of the Ekman buoyancy flux. And, I think that really reflects a sort of ongoing computational challenge we have, is how do you take these results and scale them up or scale them down, given our computational limitations. Now, the other mechanism, which is sort of familiar from larger scales, is the so-called thermal feedback. That is, it was shown at left here. So you have warm SST, you enhance surface heat fluxes out of the ocean. That drives turbulence, a deepening of the boundary layer, and an enhancement of surface winds. Now, there's lots of reasons to think that mechanism might change or differ at the submesoscale. The atmospheric boundary layer response is expected to be in disequilibrium. That's unlike how we often think about this at larger scales. So what's shown here is the ratio of essentially the mixing time scale, the vertical mixing time scale to mix throughout the boundary layer relative to the horizontal advective time scale. So in this case, that's expected to be large. That is, advection is going to be important. It'll take some time to send the signal up through the boundary layer. Advection is important in terms of the sort of dynamical response of the ABL. So if you think of a Rossby number defined using the atmospheric wind scale and then the length scale of the SST front, that's always much larger than one here, even for very small winds. That's different than how we often think about this at the ocean mesoscale and larger. And then the atmospheric aspect ratio is also not small. The height of the planetary boundary layer becomes comparable to the horizontal length scales of these fronts. And so questions about things like the role of horizontal mixing become important as well. So despite all of these sort of fundamental dynamical differences that you might expect, idealized models still show a really strong response of the atmospheric boundary layer to small scale SST perturbations. So what's shown here is an LES, so a slice through an LES of the atmospheric boundary layer. So the vertical coordinate is height above surface here. And this is forced with there's a wind sort of into the page here aloft, and then there's a cold SST region flanked by two warm SST regions. And what's plotted here is the temperature anomaly that develops. And so you see the development of this cold anomaly, stably stratified internal boundary layer over the cold SST region. And you can also get a sense in this of the sort of enhanced turbulent mixing, which is happening on the flank, sort of similar to the cartoon shown at right. And in these simulations, that changes the vertical stress divergence. So looking here at the vertical flux of a long front momentum, so V prime, W prime here. The left column is for the warm SST regions. The right column is for cold. The top row here is averaged over the first hour and then the second hour. And what you see is going from the top to the bottom over the warm SST, there's a deepening of the planetary boundary layer, or a deepening of this turbulent stress layer. That acts to reduce the stress divergence over the warm region. And then in contrast, over the cold SST, there's this sort of collapse of the turbulent mixing layer down to something like 100 meters height. That's that internal boundary layer, which develops right over the cold SST. That enhances the stress divergence, even though the sort of near boundary stress has decreased. The vertical scale has decreased so much, the stress divergence itself is much larger. And that in turn then allows the surface winds to change. And so these are two Hofmahler plots. So here's time, here's cross-frontal distance. So the cold SST region is here between these two white lines, warm on the flanks here. And there's a very rapid deceleration of the along front wind. So it starts, with wind blowing along the front that decelerates in sort of half an hour or so. At the same time, you sort of unbalance the atmospheric boundary layer and develop this cross-frontal wind. So there's a U component of the winds develop here, negative and positive. And then I'm also contouring here temperature at 10 meters. And so one thing you'll note is that there is an atmospheric response to the development of this horizontal gradient in temperature, which is first in some places offset. So it's being advected. So it's not, coincident with the front itself, the SST front, but also the atmospheric, the sort of length scale of the atmospheric response can be quite sharp, even though the boundary layer depth is tall. So even though the aspect ratio is large, there's a lot of frontogenesis that occurs in the atmospheric boundary layer due to convergent flow along here. So there's convergence of the winds that lead to a sort of frontogenesis on the atmospheric boundary layer. So you can actually get this very sharp response in temperature in the atmosphere in these simulations, despite the fact that the planetary boundary layer is relatively tall. These cross-frontal winds lead to the development of a secondary circulation. So here's height, cross-frontal distance. The black contours are the overturning stream function, and in the background is contoured the atmospheric temperature anomaly. And so there's this overturning flow. So ascending here on this, you have this horizontal convergent on the left side of this filament, ascending motions, and then descent over the divergent part of this cold filament here as well. One thing I'll note is that this response does actually extend up above the planetary boundary layer. So if you look at vertical velocity sort of up in the inversion layer, we see vertical velocities here. And actually, Peter Sullivan has a couple of papers looking in more depth at this sort of signal in various LES of winds across sharp submesoscale fronts. Often sees a stronger response than we see here as well. And so it's essentially, I think at this stage, it's fair to say it's unknown what significance this is. At larger scales, there's been some very nice work by Tom Kilpatrick and others on how this sort of response can actually generate Lee waves, a Lee wave response into the free troposphere. Here the length scales of the fronts are so small that you're not in a sort of wave making regime, you're in an evanescent limit. So just to speculate, I think it's interesting to consider whether this might act as some sort of effective form drag. That is, all this fine scale SST variability, whether it might act in some sense like surface roughness from an atmospheric perspective through these sort of changes, modulations of planetary boundary layer height. And then convective organization is another one that there's a lot of interest in as well. So these are from very idealized LES, but one of the things which I think is really exciting is new work coming out of S mode that seems to, at least qualitatively, confirm some of what we see in the LES. And so shown here at left, this is a map, so looking down, of wind stress in color from Doppler scat, so airborne observed wind stress. The wind streak lines are shown here. This track here, this is SST from a ship survey. So there's a warm region here and then a cold SST region here. And there's sort of clear modulation of the wind stress with reduced wind stress over the cold, enhanced wind stress over the warm regions. And as part of this survey, there was both sort of underway CTD. So here's depth on the ocean side and distance unraveling this survey. So warm going into cold, back to warm. And then there was also on the ship an upward looking wind cube that allowed us to see the wind speed or profiles of the wind as a function of height. So what's plotted in color scale here is the wind speed shear, and then overlaid our potential temperature from a series of radiosondes. And so what you'll see is that over the warm regions, there's sort of a warm anomaly in the planetary boundary layer extending about 100 meters up. And then over the cold regions, the atmospheric temperature is colder, and there tends to be this enhanced vertical shear over the cold and reduced vertical shear over the warm. And so this is one example of what we see sort of lots of cases like this in the S-mode data. And so we're working currently to try to understand both the sort of observed response, to what extent are the dynamics similar to what we expect? Is it similar to what we see in these very idealized LES? But then also there's really, I think, a remaining open question about how this might affect ocean dynamics. There's clearly things like a wind stress divergence in this case, often a wind stress curl introduced. And, I think it remains unclear whether that is important in light of the many other sources of very strong vertical velocity that happen at these very sharp fronts. So that's something we're working on, but it's really, I think, exciting to see observational confirmation of this sort of change in atmospheric boundary layer response showing up in the surface wind stress as well. Now, the final thing I wanted to comment on today is that, both of those prior mechanisms are focusing on changes in the surface momentum flux, but there's also this direct eddy potential energy flux, which I think tends, to be somewhat overlooked. And so this is work that Igor has led along with Lionel Renaud. It's just been submitted for JPO, and there's a preprint available if you become interested. And the basic idea is that if you have a front as shown schematically here, so warm and cold, so positive buoyancy anomalies, there'll be associated positive or out of the ocean net surface heat flux, or a loss of buoyancy through a surface buoyancy flux. In contrast, over cold, there'll be a gain of buoyancy through the surface heat flux. And so that leads to this correlation between surface buoyancy anomalies and surface buoyancy flux anomalies that acts as a direct flux of eddy potential energy. So this is essentially the eddy potential energy analog to the surface wind work. It plays the same role in the potential energy equation as surface wind work does in the kinetic energy equation. And so to look at this at the submesoscale, Igor has analyzed a set of couple numerical experiments of the S-mode region, and they're run using a coupling of WRF and Krakow for the ocean. So WRF is run at 2-kilometer resolution, Krakow at 500-meter horizontal resolution. And there's two configurations. There's a full configuration, which is fully coupled, so flux is calculated via core. And then there's a smooth version where, although Krakow is run at the same horizontal resolution, the SST field is smooth using this Gaussian filter before calculation of fluxes. So this is an example of the SST spectra, again, as seen in the flux calculation, not the total SST field, for the full in blue, and then the smooth version that the flux calculation would see. And so this allows us to, comparing the full and smooth simulations, see what role fine scale SST variability in fluxes plays in the sort of ocean energetics. And so here's the simulation domain in SST. And what's shown at right here is a spectra of the surface potential energy flux. So negative here is a loss of eddy potential energy from the ocean. And in the fully coupled simulation, this is negative. That is, it's reducing the eddy potential energy all the way through the submesoscale down to really the effective resolution of the model. But if you smooth the SST field, that is the heat flux calculation in particular doesn't know about all this fine scale SST variability, you destroy that correlation between buoyancy anomalies and buoyancy flux anomalies. And then you see that actually this starts acting as a source of eddy potential energy, in this case, to the ocean. So this change in the fluxes then shows up really throughout, sort of propagates throughout the submesoscale energetics in these simulations. And so I'll walk through this. So you'll see a series of these plots. These are cumulative spectral integrals. So starting at high wave numbers, integrating to low wave numbers, comparing the full, which is in blue. Again, that's the fully coupled, and then smooth, where the SST field is in the calculations in orange. And then in each case, the ratio of the difference, full minus smooth over the full, is shown in dash just for comparison. So again, in the full simulation, this EPE flux is a sink of eddy potential energy. In the smooth, it's sort of a negligible term. And so comparing the eddy potential energy between the two, you see about a 10 to 25% reduction in EPE due to this eddy potential energy flux. That in turn changes the conversion of eddy potential energy to eddy kinetic energy. So if you look at the vertical buoyancy production, these are all average over the mixed layer. You see a reduction of vertical buoyancy production by about 10 to 25% in the case where you have this fully coupled run compared to the smooth. That shows up again in the eddy kinetic energy. So there's a reduction of about 10% in EKE in the fully coupled run versus smooth. And then finally shows up again in the wind work. So there's actually a reduction of the loss of eddy kinetic energy through the surface wind work by about 15 to 30%. So it's really, this change is coming, the numerical experiment is set up to really just change the EPE flux, or that's the most direct effect. And then it sort of propagates all the way through these pathways of submesoscale energetics. These changes are very comparable to the magnitude of changes that have been seen in this region for just looking at the surface wind work effect. So Lionel has a paper from 2018 playing with turning on and off the current feedback, and you find very similar magnitude responses. So in this case, I think for this region, at least, the direct eddy potential energy flux is as important at these scales as the eddy kinetic energy flux. One thing which I'll note as well is that really the important part of the buoyancy flux, the part that's correlated with the surface buoyancy anomaly, is the latent and sensible heat fluxes. So to good approximation, you can think of this eddy potential energy flux as proportional to the surface buoyancy anomaly and the surface temperature anomaly. Now, in this region, there's a lot of partial compensation of density or buoyancy anomalies by salinity. And so that is actually acting in this case to reduce the efficiency or effectiveness of this mechanism. That is, for a given temperature anomaly T prime, you have less of a buoyancy anomaly because there's a partial compensation by salinity. So even though there's this partial compensation of salinity in this region of the California current system, we still see this as similarly strong as the direct flux of eddy kinetic energy. In regions where there is not this partial compensation, we expect this mechanism to become even more important. And there is even the possibility of this changing sign. So if you have a salinity-dominated front, where the gradient is dominated by salinity rather than temperature, all of these arrows change sign. So the heat flux that's generated will tend to increase the buoyancy anomaly rather than decrease the buoyancy anomaly. So this is not, doesn't have to be a loss of EPE. It's only a loss of EPE in the cases where temperature essentially controls the buoyancy anomaly of the surface. It could also be a gain term as well. So just to summarize, I think it's useful to start thinking about, how we want to define an air-sea interaction submesoscale. Dynamical definitions are good, but the air, atmosphere, and ocean are interacting through what they see on the boundary in terms of length scales, and they are responding differently because of these differing dynamical regimes. Examples I gave today, so the current feedback on stress, which has been sort of well studied for the wind work effects, also at submesoscale fronts acts as a source, if you will, of Ekman buoyancy flux, or a source of PV, which is speculated to be important for frontal dynamics, not yet shown. We've had evidence from high resolution models, but now observations of this thermal feedback on winds also active at submesoscale fronts, despite the fact that the length scales are quite small relative to the planetary boundary layer height. But it really is, I think, fair to say that it's not yet clear what effect, if any, this really has on submesoscale processes. Are there coupled feedbacks because of this? I think the answer is we don't know. And I sort of ended with this discussion of how actually the direct flux of eddy potential energy is also quite important for submesoscale energetics in these simulations, comparable to the flux of kinetic energy through the surface wind work, which has been much more extensively studied. So these papers and several other relevant ones, you can all find them, including preprints via my website. So thanks again. I really appreciate the opportunity to talk.
Well, thank you so much. And questions for Jacob? So maybe while people are thinking, I will ask about the question you raised about a question implicit in the final example you showed about scales. So I guess I'm wondering, you have Whorf and Krakow at different resolutions. You've showed that filtering has a big impact on the coupling. Does it matter that the models are actually configured at different resolutions? And
yeah, so I think the sort of reasoning around that is that the model effective resolution is, a multiple, probably eight times the grid resolution or the grid spacing. And so, although we run at 500-meter horizontal resolution, we don't actually resolve variability down to 500 meters. It's probably resolved down to about 4 kilometers or so. And because the atmospheric model, which is run at 2 kilometers, just feels the SST variability as fed to it, it actually sort of makes sense in a way to run the atmospheric model, which is quite expensive at lower resolution, because we don't, you could run both at 500-meter resolution, but your ocean model is not going to create the variability that should be there at that scale anyway. Now,
Thanks.
does it go the other way? I think, I'm not as sure about.
So I see that Claudia has her hand up.
Thanks, Jacob. Very interesting talk. Lots of things. So it will take some time to digest everything. So I would like to go back to what you said about the idealized LES simulations, where you put a cold patch in the center, and you show the change in the along front wind, but then you also show the creation of a cross frontal wind, and that had an asymmetry. Can you elaborate a little bit on that asymmetry in the cross frontal wind?
The asymmetry in that, why does it rotate in the direction it does over warm versus cold? Is that?
I mean, if I well understood, the cold patch is located at the center, right?
Yeah.
And on the side, you have the same temperature, warm temperature on both sides. But there was a left and right asymmetry, and I was wondering where it's coming from.
Yeah, so in particular, yeah, right. So there is an advection off, sort of off the front on the left side, and not so much on the right side. Is that what you're getting at? Yeah, I think that has to do a lot with the development of this secondary circulation. So this sits here at this descending branch of that circulation. And so we do in the paper sort of parse out the momentum budget, and the sort of momentum flux associated with that is important and changes it. And that leads to this sort of offsetting where there's not strong frontogenesis here. So this structure is being strongly forced by the SST field. This sort of horizontal length scale, is sort of an imprint of the length scale of the front, which is shown in the solid white bar here. Whereas this side, first, what happens is there's a lot of frontogenesis that plays a major role in setting this scale because of the convergent flow. because of this rotation of the winds when you unbalance it. And then later in the simulation, you also get a role for horizontal mixing, sort of arresting and spreading that as well. There's very reasonable questions, I think, about, how much we can take from this sort of very idealized single frontal simulation, how general these results might be, particularly in the late time evolution. I think it's a little less relevant here, but I think the first several hours are fairly relevant.
What's asymmetrical about the system? Because you didn't really answer, you just said there's an asymmetrical secondary circulation. What sets the asymmetry?
Well, so it's a doubly periodic domain, and so we set this up by spinning it up over homogeneous SST, and then you develop an Ekman near surface Ekman layer, and then we basically put the fronts in so that we have our 10-meter winds down the fronts. As soon as you change the turbulent mixing profile over both warm and cold, you've broken the initial Ekman balance, and that tends to lead to this counterclockwise rotation over the cold and clockwise over the warm. So just because we are doubly periodic, one side will be convergent and the other side will be divergent. It's a doubly periodic domain, so that has to, be closed with this closed secondary
So
circulation.
there's a wind direction, and plus the Earth's rotation sets the asymmetry.
That's right. Yeah.
Okay,
yeah.
so it's the atmospheric analog of up front, down front.
That's right. Yeah, I think that's a
Okay.
fair way.
Okay. But that wasn't my question.
Okay, what's your question?
First one was about symmetric instability, which you talked a little bit about. And I guess the way that I've always thought about it is you have a turbulent boundary layer. Sometimes it's forced by convection, sometimes it's forced by winds, sometimes it's got a wave component, sometimes it doesn't. And when you add in symmetric instability, it's just another form of atmospheric boundary layer. In other words, there's now a geostrophic shear production component, and therefore the structure of the boundary layer look different, but it should be thought of in terms of boundary layer dynamics, not as there's laminar symmetric instability plus Kelvin-Helmholtz. No, in fact, it's the whole thing's turbulent. It's a turbulent boundary layer affected by the fact that there's a lateral buoyancy gradient. Do you think that that's the right way to think about it?
Yeah, I think I understand where you're going with that. So, I mean, right. So there's a new production term, which is in the TKE budget, which is the geostrophic shear production. And, a good assumption is to say that the thermal wind shear is sort of vertically uniform throughout the boundary layer. So it's all set by, V prime, W prime. And that has components both at what you might call the submesoscale from the actual overturning circulations, but also finer scale things. So in some sense, I've often thought of SI as being sort of the most, almost like a coherent structure in boundary layer turbulence, less submesoscale-ish as some other instabilities. And so, yeah, I think you could usefully just say, okay, there's a TKE budget which spans from the overturning cells down to very small scales, and it doesn't really matter where the partitioning is between the overturning cells and the KH, say, instability. One place it does maybe matter, so that the sort of figures that I used there were from a paper by Thomas Schor from last year, and he is able to show that actually the mixing efficiency as you go from symmetric instability to more sort of centrifugally dominated instability can vary, and you can understand that variation from the literature on the mixing efficiency of KH instability. So it's sort of like you set up the secondary instabilities, KH, feel the background state set by SI or centrifugal instability, and that then changes their evolution a bit. But yeah, I think you're fundamentally right that SI is something that really blurs the distinction between boundary layer turbulence and
because the mixing efficiency is different in a convective boundary layer and a shear driven boundary layer too. So sure, different things change. Okay, cool.
Yeah.
Looks like Megan Cronin has her hand up.
Hi, Jacob.
Hi, Megan.
My question is, can you talk about how these processes might work in the tropics versus the extratropics, and the relative importance or response to these kind of submesoscale fronts?
Yeah, I probably not sensibly enough. I mean, I think that is one of the reasons to use a dynamical definition of the submesoscale, right? So, Ryan Holmes and others have, I think, done nice work on things like TIWs in terms of, seeing them as submesoscales, and that's useful. So certainly this sort of idea of just using length scales fails as you move, between the tropics and mid latitudes and high latitudes. I'm a little less confident trying to answer it from an air-sea interaction perspective. But if you have thoughts, I'd love to hear them.
Well, only that we do get very sharp fronts in the tropics, as well as in the extratropics. And so, yeah, no, I don't have a really good answer yet. But, the fact that, your Ekman buoyancy flux is going to really change as you go towards the equator. And so that will cause a big difference, and then time scales too. But I don't, so I was hoping that you might.
Yeah, not off the top of my head. I will think a bit more about it. It's an interesting question.
Right.
Looks like Shikar is next.
Hi, Jacob. Very nice presentation. I got to learn a lot from this. I was wondering about the secondary circulation because of the warm core, cold core eddy. So many literature show that the small scale winds and small scale ocean currents are like positively correlated. Is it possible that because of this warm core or cold core eddy, that the secondary circulation could reduce this positive correlation? Because clockwise rotating warm core eddy could generate counterclockwise secondary circulation in the atmospheric boundary layer. Is it possible to happen such?
Yeah, I mean, I do believe that there's been some recent work. Is it Contreras et al. 2023? Igor, you would know better than I. Leonella is one of the co-authors on that. Actually, that does seem to show that that the thermal feedback itself acts as a sort of source of positive wind work at these scales. So, you think of the current feedback effect as negative wind work, a loss of eddy kinetic energy, but when you include the thermal feedback, that partially offsets that. So I think that maybe is the sort of that does not necessarily involve the development of sort of a secondary atmospheric circulation. You could just, use vertical momentum mixing or one of the other sort of classic ways that you change winds, but it is of the sense to do positive wind work.
Thank you.
So it looks like Igor has put the paper in the chat if anybody wants to track it down. And Rick Danielson has a question in the chat. Rick, do you want to ask it or should I?
Yeah, just a quick, I don't know if you can hear me. Sorry, I just
Yeah.
pressed the right button, but just whether we do have lots of review of air-sea interaction in general. So I'm just wondering if you could comment on sort of dynamical definitions of mesoscale and synoptic air-sea interaction in the context of the submesoscale.
Yeah, I mean, I think I guess I would turn that question around to answer it in terms of what's different at the submesoscale, right? Which is, I think, this idea that, first of all, you can't rely on assumptions of equilibrium response of the atmosphere. So the time scales are fast, the length scales of disequilibrium sort of span at least partially into the ocean mesoscale, but certainly in the ocean submesoscale. And then these issues of things like the aspect ratio being small. So really, I think many of our conceptual or dynamical models of the processes of air-sea interaction tend to rely on assumptions which are most definitely violated as you get to these smaller scales. Now, it is an open question. I think, we can get a lot of insight from theories that are violated in various ways, and they often still work pretty well. And so for example, the thermal feedback sort of simulations and some of what we see in the observations at first pass seem quite consistent with what you might expect from all the work at larger sort of, mesoscale, ocean mesoscale, and larger scales. So I think it is an open question, at what level those sort of modifications matter. The other part of the answer I guess I'll give is, part of what I hope I've emphasized is that many of the sort of ideas about how air-sea interaction modify ocean dynamics rely on things like the generation of, wind stress curl is a nice example, right? So, you introduce small scale variability into the wind stress, and there's now wind stress curl that wasn't there before. Naively, you could say, okay, well, the wind stress curl depends, inversely on the length scale that is happening over. So we'll go to submesoscale, and this will get a lot stronger, and so it's more important. And that is true, it will get stronger, but at the same time, you really shift dynamical regimes, and all of a sudden you go into, submesoscale frontal circulations that can have, 1,000 meter per day overturning circulations. And I think we have not yet fully determined whether the relative importance of these mechanisms change as you go down in scale. So, you increase the magnitude of things like the wind stress curl, and so Ekman pumping, but you also introduce a whole host of other processes that start happening. So part of the work on the Ekman buoyancy flux was, hopefully to sort of start working down that road. That is, this is a quantity that doesn't really perhaps matter at the larger scale, but is known to be very important at submesoscale fronts. And Larry has added in the chat. Yeah, so Larry was really was one of the co-chairs of this workshop at the Lorenz Center, and has been really involved in this ASI idea. We hope to have a white paper out soon. And so we definitely circulate it with this community for input as well.
Other questions?
Well, I'll add one more unless somebody else has one. Say too much.
Go ahead, Eric.
I always say too much. When you think about this problem from a big point of view, from a coupled boundary layer point of view, which I really like that way of thinking about it, I'm not even sure we know quite how to think about it. But one of the questions that always occurs to me is you want to know how the ocean variability, and I'm specifically thinking about this for submesoscale, so it's phrasing it broadly, how that affects the vertical velocity at the top of the boundary layer, because that's what makes convection and other things. In other words, boundary layer, you can get all sorts of flows. They go round and round in the atmospheric boundary, saying maybe you don't care that much, but you certainly care if there's net export of moisture from the atmospheric boundary layer. So I wonder if you've thought about whether there are essentially rectified effects. I'm saying it wrong. And what aspects of these things that you're talking about end up promoting net convergence in the atmospheric boundary layer, and therefore essentially convection. And there's an inverse problem for the ocean, of course, going both ways.
Yeah. Right. So it is definitely clear that the say the vertical velocity in above the planetary boundary layer, that the response is not symmetric if you're going from warm to cold or cold to warm. So I think that sort of feature, we see that. So Peter Sullivan has a series of 2 papers, 2019, 2020, or 2020, 21, looking at this problem in detail. And I think that suggests there can be or will be rectified effects, right? So it won't average out. that was the subject of a lot of conversation, particularly around problems like at this workshop. You know, does it contribute to convective organization? My impression, and if there's others on this call who know better, they can correct me, but my impression was this is something that actually hasn't been explored from the atmospheric side, that there's been a lot of work on kind of self-organization of convection, you know, over homogeneous SST, but that people haven't yet done the sort of simulations that you would want to do to figure out how this might aggregate. So yeah, it's the right question, but I don't think there's an answer yet.
Well, thanks. If other people don't have questions, I wanted to return to the satellite question that you indicated at the beginning you maybe weren't addressing, but based on this discussion, what do you think the resolution requirements are to observe the types of phenomena that you're looking at?
Yeah, that's a good question. I mean, you know, so the Ekman buoyancy flux remains challenging from satellites because of the lack of salinity information, right? You can do the heat flux or the temperature flux part of it.
Hard to get high resolution salinity, yeah.
Right. So, you know, having higher resolution winds would allow you to start looking at the thermal feedback. And, you know, I think, to be honest, going into S mode, for example, part of my expectation was that we would not see such a strong response at these scales, because although we see it in these idealized simulations, you know, often if you imagine the sort of residence time of an air parcel over these frontal features, it's quite short. And so presumably in the Lagrangian frame, you're just seeing lots of different fronts all very quickly. And so to see such a strong response was surprising. I think that suggests that there's probably a, you know, pretty, that, you know, you could get, we know we see it at sort of, you know, 1 kilometer scale, and we know we see it at 30 or 50 kilometer scale. So it's presumably everywhere in between. So the finer you get, the more you'd see of that. The eddy potential energy flux is also, you know, of course, active at the mesoscale. And so Stu Bishop has papers on that. And, you know, essentially the ratio of the importance of the flux of eddy potential energy to the wind work goes like the eddy potential energy, surface eddy potential energy over the surface eddy kinetic energy. So Igor sort of lays out a scaling argument for this, trying to understand how this might be more general. So I do think that this eddy potential energy part of the story may have a scale dependence relative to the eddy kinetic energy, probably scale and regional dependence as well. So that's not really an answer to your problem, in that I'm not giving you sort of length scales, but you know, maybe the answer is, from my perspective, the finer the better, but you know, the sort of mechanisms are probably there at all scales. So anything you can give us would be good.
That's a good answer. Anything else? I saw Igor put your camera on. No. Well, thank you very much for this webinar. Thanks everyone for participating. And one minor announcement. I think that we don't have a speaker for next week. And I think that OASIS is looking at coordinating special sessions for the AGU meeting, and wondering if anybody wants to help convene. So if you're interested in that, contact Megan Cronin.
Thank you. Really appreciate it.
Thanks a lot. Bye.